Okay, so we are starting chapter 8 today. We're going to talk about what's called the mathematics of scheduling, which, just like it sounds, we're going to make some schedules and kind of look at the mathematics behind how to make effective schedules versus ineffective schedules and that kind of stuff. In this section, this is really just the intro section. We're going to get into a number of definitions. We're going to also get into some of the assumptions that we're going to have to make in order for this to work. So a little bit more definitions today, a little bit less practice that we're going to be doing, a little bit less math that we're going to be doing. That'll all come in the later sections. So first things to talk about are principal characteristics of scheduling. Let's talk about the processors. So the processors are basically the workers. We just use this to describe anyone that's going to be doing the job. It doesn't necessarily have to be humans, although that's usually the way we like to think of it. It could also be a robot, it could be a computer, an ATM, so on. When we do talk about that, we are going to use this notation with N to represent the number of processors, and then we'll label those as P1, P2, P3, and so on, as you can see right here. Also, we're going to assume that there's always going to be at least two processors, so n is going to always be at least greater than or equal to 2. With there being just one processor, it's not really all that exciting. You don't really get to see a lot of the cool stuff that can happen unless you have at least 2. The second thing we're going to have is the tasks. So every project we're looking at are broken up into individual pieces, which we're going to call either jobs or more commonly tasks. So we're going to define a task as an indivisible unit of work. In other words, by nature or by choice, it cannot be broken up into smaller units. That being said, then a task can't be shared. So when you have a task, it's either carried out by one processor or the other, but you don't have shared work, I guess is what we're saying when we talk about our tasks. We'll usually use abbreviations that are just kind of convenient. We don't have a labeling system like we did for processors, calling it P1, P2, and so on. For example, we might use capital WE for something like wiring the electrical system, where W for wiring, E for electrical. We just kind of use whatever is convenient. So when we have a task that needs to happen, there are basically 4 stages that it can be in. The first is that it's ineligible, meaning that the task cannot be started because something else has to happen first in order for it to be completed. The second is that it's ready. That means that it hasn't been started yet, but it's currently ready to go. There is not anything holding it back. The third is in execution, meaning that the task is currently being carried out by one of the processors, but isn't finished yet. And the last is that it's completed, which again should be kind of common sense. The task is done. In addition to those, we're going to have what are called processing times. So a processing time is the amount of time that it takes for a given task to be completed. For example, if we were thinking about the wiring, the electricity, which we call WE, maybe that would take a couple hours to do. So after the WE for your task, in parentheses, we'll put a number. That number that goes in the parentheses can be hours, minutes, days, whatever it might be that you're talking about in that situation. Now, let's assume that we have robots as our processors. And again, the reason why we're going to do this is because robots obviously can carry out a number of different tasks and are going to be standardized. We could also think of them as very well-trained people. So if a person was very well-trained to work in a very uniform way, then we could also think of it as a human. But oftentimes it'll probably be better to think about these tasks being processed by robots. And so here are some assumptions that we're going to make. These are key assumptions. Obviously, this does not always happen in the real world, but in order for all of the kind of math that we're going to look at to make sense, we're going to have to assume these 3 things. The first is that any processor can execute any task. We call this the versatility assumption, meaning that basically anyone can do anything. There is no specialization. Every task can be processed by any processor at an equal rate. And that's the second assumption, actually. The processing time for a task is the same regardless of which processor is executing the task. Again, this is why we kind of think of it as robots or being robotic, is that a robot could obviously carry out a task in the same amount of time as any other robot would or any other computer would. Again, assuming that they can do it. This is the uniformity assumption. The last thing is once a processor starts a task, it will complete it without interruption. It's not going to take a break in between. It's going to continue to work on it. We'll call this the perseverance assumption. So again, after looking at these, you can see that these would not always be the case in a real world scenario. Do people need breaks in between jobs? Yeah, oftentimes they do. Can all of the people do the same job in the same amount of time? Well, some might be able to do it quicker, some might be able to do it slower. Obviously, when you think about it, there are a lot of variables you'd have to consider. So thinking about it in terms of a computer carrying out the tasks or some kind of a robotic element in there will help you to kind of remember these assumptions that we're making in order to make everything else kind of work for us. All right. This slide, I'm not going to read through the whole thing. It just kind of reminds you of that notation that I used earlier where you list the task and then in parentheses put the processing time, which remember with that being units, and that could be minutes, hours, days, any other unit of time we'd want related to whatever tasks we are looking at. So part of scheduling that we need to discuss is what are called precedence relations. Basically what that means, and when you think of the word precedence, it means that something has to happen before something else can occur. Typically we would say that X precedes Y, or that if you want to think about it as a prerequisite in terms of a class for like the school classes, you obviously have to take Algebra 1 before you can take Geometry, before you can take Algebra 2. Those are the kind of precedence relations that we're going to be talking about. Now, the way we write those is by using this abbreviation, pretty convenient. X precedes Y is written as X with an arrow pointing towards Y. Or if you think of it on a graph, you can think of it kind of the same way. In other words, a lot of that stuff that we've been looking at in terms of graph theory, we've just had these connections where you could go from X to Y or Y to X, and it really didn't matter which direction you chose. Now we're saying it does, that if X precedes Y, then you have to do X before Y. So now we have these directed graphs, which is what we'll talk about more in actually section 8.2. So again, some more information on that. Oftentimes, there's also no restrictions that are placed on two tasks, in which case you would say that they do not have any precedence requirements. And if that's the case, then tasks are independent. You really don't have any arrows between them. Graphically, here's what it looks like when two tasks are independent, is when there aren't any arrows connecting the two. So some properties of this. Precedence relations are in fact transitive. In other words, if X precedes Y and Y precedes Z, then it must be true that X precedes Z. And again, when you're looking at those arrows, and I'm reading those as precedes, against precedence relationships, then that's kind of how you'll read those. And hopefully this graph kind of makes sense. If you have to do X before you can do Y, and you have to do Y before you can do Z, then you obviously can't just go from X to Z. You have those in-between steps, but it does mean that X has to happen before Z. It's not like you could do Z before X. So that's kind of implied when you're looking at a relationship like this. Now, another characteristic is we're not going to actually have any kind of circles or cycles or circuits. If X had to happen before Y, and Y had to happen before Z, Z before W, and W before X, then pretty clearly this is never going to be able to happen because you have to have somewhere to start. And so you can't have a cycle because it obviously would not work in terms of what we are discussing. So let's take a look at an example of kind of all of this in practice. Let's imagine that you just wrecked your car. Obviously you're okay. Insurance company is going to pay for everything. You just have to wait for the car to get fixed. So you take the car to the best garage in town, operated by the Tappet brothers. We'll call them, they're Click and Clack. We're just going to call them P1 and P2 using the notation we talked about earlier. And the repairs on the car can be broken into 4 tasks. You've got task A, which is that the exterior body work, it's going to take 4 hours. Task B, the engine repairs are going to take 5 hours. Task C, painting and exterior finish work, is going to take 7 hours. And D, transmission repair, is going to take 3 hours. Now, the only precedence relation that we're going to have for this is that the painting and exterior finish work cannot be started until the exterior body work has been completed. In other words, that A precedes C. The two brothers always work together on a repair project, but each takes on a different task, so they won't argue with each other. Under these assumptions, how should the different tasks be scheduled? Who should do what and when? Well, let's take a look at some possibilities. So here's one possibility. You've got a schedule, but not very efficient. If you look at it, it's going to take 12 hours to complete this project. Processor 1 gets all their stuff done in the first 7 hours, whereas processor 2 has to go the full 12 hours, and that's a lot of idle time. You want to try to minimize the amount of time that's idle between your processors. So let's maybe look at a different scenario. Much better in this scenario, right? We went from 12 hours of completion now down to 10 hours where it's going to be completed. We'll use this notation FIN to denote our finishing time. Obviously, for the first project, we had a 12-hour completion. Here is what it looks like. But the problem with this one, and maybe you didn't notice it yet, maybe you did already, which is great, is that remember that A has to come before C. You have to finish your exterior body work before you can do the exterior paint job. And so if A has to come before C, if A is still happening right in here, then you can't have C happening yet. In other words, this would have to be the starting point of C if we were going to do it this way, and that's going to take an extra time slot right here to be able to finish C, which actually is what ends up happening. If we were to make our second processor wait for an hour for the first processor to finish that project A, then we can start task C, and this is a perfectly fine schedule. Notice that, like I mentioned, it does mean that you extend from it finishing in 10 hours to 11, but 11 is a lot better than finishing in 12. So, obviously, schedule is an improvement. Can we do even better, though? It turns out no, actually. No matter how clever we are, and no matter how many processors we have at our disposal, that precedence relation of A having to come before C means that 4 plus 7 is 11. It's going to mean that you have to have at least 11 hours to complete the job. No matter what you do, you have to have 11 hours because A has to work, then C can work, and so that's going to be the minimum amount of time that we need in order to complete the job. So obviously that was an optimal schedule. Here is another optimal schedule that you could use instead, and this is, again, with a finish time of 11 hours. When we have the optimal schedules, we will sometimes use OPT in place of FIN to indicate that it's the optimal finishing time as opposed to just any old finishing time. So, as far as scheduling goes, that was a pretty simple one. You only had 4 tasks, 2 processors, it's pretty easy to figure out. But as we get into more complicated cases, we're going to need a lot more help with determining how to make the schedule. Obviously, with smaller examples, you can kind of do that trial and error method that we just did, but we're going to need some scheduling algorithms to go into our tool belt as well as all of the other algorithms that we've seen in the previous chapters. The second thing to talk about is that there's going to be an absolute minimum time that no schedule can break no matter how good we are. We're going to call that absolute minimum time the critical time. In other words, this is the amount of time that it would take for the project to finish, and this is the absolute minimum amount of time that we'd have to use. So in the previous example for 8.1, we would say that the critical time was the 11 hours, which was also the optimal time. So let's get into a more complicated example. And in fact, we're not even going to be able to finish this one today. We will by the end of this chapter. So we're going to be referring back to this quite a bit over the next few videos. So imagine it's the year 2050 and several human colonies are being established on Mars. Imagine that you have accepted a job offer to work in one of those colonies. Well, where are you going to live? Like everybody else, you're going to be provided with a living pod, which is called a Martian Habitat Unit, or MHU. MHUs are shipped to Mars in the form of prefabricated kits that have to be assembled on the spot, which can be an elaborate, very unpleasant job if you're going to do it yourself. So we're going to have some robots help us. A better option then is to use these specialized construction robots that can do all of the assembly tasks much more efficiently than human beings can. These construction robots can be rented by the hour at a local rent-a-robot outlet. The assembly of an MHU consists of 15 separate tasks and 17 different precedence relations. The tasks, their respective processing times, and their precedent tasks are all shown on the next couple of slides. So here are all the tasks that are going to happen, as well as their labels and their processing times, as well as any precedent tasks. So obviously, assembling the pad, you don't have to do anything else before that. Same with flooring, wall units, and dome frame. But when you're ready to install the floors, you have to assemble your pad and your flooring first, obviously, before you can install the floors. So 2 precedence tasks for that. And then you can see as we get into some of the other tasks, there's going to be quite a bit going into this problem. So here are some of the basic questions that you want to start to think about that we're going to be discussing over the next couple of videos. Number 1, how can we get our MHU built as quickly as possible? Number 2, how many robots are we going to need to rent in order to do the job? Third, how do we create a suitable work schedule that's going to get the job done? Obviously, a robot's going to do whatever it's told, but someone has to tell it what to do, and they have to say when. These are all very hard questions to answer. We're going to be talking about them over the next couple of videos, the next couple of sections. Until next time, guys, have a good rest of your day.